Load factor is a measure of how consistently a load is utilized over time. It is defined as the ratio of the average load power over a given period to the peak load power during that period. A load factor of 1 indicates that the load is always at its peak, while a load factor of 0 indicates that the load is never used. The values for load factor given in IEC load studies are derived from statistical analysis of actual load data. These data are collected from a variety of industrial, commercial, and residential customers. The analysis determines the probability distribution of the load power over time. The load factor is then calculated as the ratio of the mean load power to the maximum load power. The range of load factor values given for typical 415 volts, 3-phase kilowatt motor loads, which is 0.7 to 0.99, is based on the analysis of actual load data from various industries. The specific value for a particular motor load will depend on the type of motor, the operating conditions, and the load profile. The following equations are commonly used in IEC load studies to calculate various load parameters. Firstly, consumed load factor in kilowatts equals absorbed load divided by efficiency. This equation calculates the actual power consumed by the load. Secondly, load factor equals absorbed load divided by load rating. This equation calculates the ratio of the actual load power to the rated load power of the motor. And thirdly, absorbed load equals load rating multiplied by load factor. This equation calculates the actual load power based on the load rating and the load factor. Understanding these equations is essential for accurately assessing load requirements and optimizing energy consumption in electrical systems. Load factor plays a crucial role in designing efficient and reliable electrical systems. By understanding the principles behind load factor and its derivation, engineers can make informed decisions about equipment selection, sizing, and operational strategies. Let's delve deeper into the significance of load factor in various applications. In industrial settings, load factor is used to evaluate the performance of manufacturing processes and machinery. High load factor indicates that equipment is being utilized effectively, minimizing idle time and maximizing productivity. Conversely, a low load factor may suggest inefficiencies in the production process, such as underutilized equipment or frequent start-stop cycles. By analyzing load factor data, engineers can identify areas for improvement and implement strategies to optimize energy consumption and reduce operating costs. In commercial buildings, load factor is used to assess the energy efficiency of lighting, heating, ventilation, and air conditioning, also known as HVAC systems. A high load factor indicates that these systems are operating efficiently, providing consistent comfort levels while minimizing energy waste. A low load factor may suggest inefficiencies in the design or operation of these systems, such as oversized equipment or inadequate controls. By monitoring load factor trends, building managers can identify opportunities to improve energy efficiency and reduce utility bills. For example, implementing occupancy sensors, upgrading to energy-efficient lighting, and optimizing HVAC controls can significantly improve load factor and reduce energy consumption. In residential applications, load factor is used to evaluate the energy usage patterns of households. A high load factor indicates that residents are consistently using electricity throughout the day, while a low load factor may suggest intermittent usage patterns. By analyzing load factor data, utility companies can better understand the energy demands of their customers and develop targeted energy efficiency programs. For example, offering rebates for energy-efficient appliances, providing tips on energy conservation, and implementing smart grid technologies can help residential customers improve their load factor and reduce their energy bills. In addition to its role in energy efficiency, load factor is also important for grid stability and reliability. Utility companies use load factor data to forecast electricity demand and plan for future capacity needs. By accurately predicting load patterns, utility companies can ensure that there is sufficient generation capacity to meet the demands of their customers. This is particularly important during peak demand periods such as hot summer days or cold winter nights, when electricity usage is at its highest. Load factor also plays a role in optimizing the operation of power generation facilities. By understanding load patterns, utility companies can schedule maintenance and repairs during periods of low demand, minimizing disruptions to the electricity supply. In addition, load factor data can be used to optimize the dispatch of power plants, ensuring that the most efficient and cost-effective generation resources are used to meet electricity demand. The concept of load factor is closely related to other important metrics in electrical engineering, such as demand factor and diversity factor. Demand factor is the ratio of the maximum demand of a load to its total connected load. It represents the percentage of the total connected load that is actually being used at any given time. Diversity factor is the ratio of the sum of the individual maximum demands of a group of loads to the maximum demand of the entire group. It reflects the fact that not all loads will be operating at their maximum demand simultaneously. Understanding the relationship between load factor, demand factor, and diversity factor is essential for accurately assessing the overall electrical load of a system. These metrics are used to determine the appropriate size of electrical equipment, such as transformers, circuit breakers, and conductors. In summary, load factor is a crucial metric for evaluating the energy efficiency, grid stability, and overall performance of electrical systems. By understanding the principles behind load factor and its derivation, engineers, building managers, and utility companies can make informed decisions about equipment selection, sizing, and operational strategies. In conclusion, the effective management of electrical loads relies heavily on understanding and applying the concept of load factor. It's not just a number, it's a key indicator of how efficiently electrical resources are being utilized. As we've explored, a higher load factor generally indicates more consistent and efficient use, while a lower load factor points to potential inefficiencies. Here are some final thoughts on optimizing load factor in various contexts. For industrial applications, continuous monitoring and analysis of load factor can reveal opportunities to streamline processes and reduce energy waste. Implementing strategies like load shedding, where non-essential loads are temporarily reduced during peak demand periods, can significantly improve the overall load factor of a facility. Similarly, optimizing motor performance by ensuring proper sizing, maintenance, and control can contribute to a higher and more consistent load factor. In commercial buildings, integrating smart building technologies can enable automated control of lighting, HVAC, and other systems based on occupancy patterns and real-time demand. This not only enhances energy efficiency, but also helps maintain a more stable and predictable load factor. Encouraging tenants to adopt energy-saving practices such as turning off lights and equipment when not in use can further improve the building's overall load factor. For residential customers, promoting energy conservation awareness and providing incentives for energy-efficient appliances can lead to more responsible energy consumption habits. Educating consumers about the benefits of using programmable thermostats, energy-efficient lighting, and smart power strips can empower them to manage their energy usage more effectively and improve their load factor. Utility companies play a vital role in promoting load factor optimization through various initiatives. Implementing time-of-use pricing, where electricity rates vary depending on the time of day, can incentivize customers to shift their energy usage to off-peak periods, thereby improving the overall load factor of the grid. Investing in smart grid infrastructure, such as advanced metering infrastructure and demand response programs, can enable more efficient monitoring and management of electricity demand. Furthermore, supporting research and development of energy storage technologies, such as batteries and pumped hydro storage, can provide valuable tools for smoothing out load fluctuations and improving grid stability. In addition to these practical strategies, it's important to consider the broader implications of load factor in the context of sustainability and environmental responsibility. By optimizing load factor, we can reduce our reliance on fossil fuels, lower greenhouse gas emissions, and contribute to a cleaner and more sustainable energy future. Investing in renewable energy sources, such as solar and wind power, is essential for diversifying our energy mix and reducing our carbon footprint. However, it's equally important to ensure that these renewable resources are integrated into the grid in a way that maximizes their efficiency and minimizes their impact on grid stability. Load factor analysis can help inform the design and operation of renewable energy systems, ensuring that they are optimized for local load patterns and grid conditions. The future of load factor optimization lies in the integration of advanced technologies, data analytics, and collaborative partnerships. By leveraging the power of the Internet of Things, artificial intelligence, and machine learning, we can gain deeper insights into energy usage patterns and develop more sophisticated strategies for managing electrical loads. Collaboration between utilities, businesses, and consumers is essential for creating a culture of energy efficiency and promoting responsible energy consumption habits. By working together, we can build a more resilient, sustainable, and affordable energy system for future generations. Load factor is a fundamental concept in electrical engineering with far-reaching implications for energy efficiency, grid stability, and environmental sustainability. By understanding the principles behind load factor and implementing strategies to optimize its value, we can unlock significant benefits for businesses, consumers, and the environment. As technology continues to evolve and new challenges emerge, the importance of load factor optimization will only continue to grow. By embracing innovation, fostering collaboration, and prioritizing sustainability, we can create a brighter and more efficient energy future for all. In conclusion, remember that load factor is more than just a technical term. It's a key to unlocking a more sustainable and efficient energy future. By understanding its importance and applying the strategies discussed, you can make a significant contribution to optimizing energy use and reducing environmental impact.